So in the last session we studied the speed torque characteristics of a DC shunt motor. Today we'll be looking at the speed control strategies for the shunt motor. How we can control the speed of a DC shunt motor. So there are actually three methods by which we can control the speed of a DC shunt motor. One is by adjusting the field resistance. So by changing the field resistance we can basically change the current in the field circuitry and therefore change the field flux. Fine. So this is one method. Second method is adjusting the terminal voltage or changing the terminal voltage. So the voltage, DC voltage supply that we are actually feeding to the motor, we can vary that. And this is actually going to the armature. So one is field control method. Field control method basically involves changing the field resistance, and another one is the armature control method. The armature control method involves basically changing the voltage supply to the armature of the DC motor. One more method that we can actually use for speed control, but it's not much used, is changing the armature resistance. So we have three methods: adjusting the field resistance, varying the terminal voltage of the to the armature, feeding the armature, or changing the armature resistance. This is not a preferred method of controlling the speed of a DC motor. Fine. So first of all, why do we need to control the speed of a DC motor? We have various applications where, say for example, in a common household application, that is a fan, we need to control the output of the we control the speed of the fan so that accordingly the air can be circulated in the room. So there is not a DC motor in your household in a residential fan, but there are applications similar to that where DC motors are used, like in case of traction systems, like in case of monorails. Fine, you can have DC motors used to drive the train. So we want to control the speed of the drive. We want to make sure that it is moving quickly, it comes to halt at a certain place. Therefore, being able to control the speed of the DC motor, and that also efficiently, is a requirement. And these systems that basically control the speed of any motor is referred to an electrical drive, and we'll be studying different control strategies in different types of electrical machines for speed control. So in every motor, one of the main features is having the ability or offering the ability to control its speed. Fine. We have three methods here for DC shunt motor. Now discussing the first one. So adjusting the field resistance. what happens by adjusting the field resistance is will be actually changing the field current and therefore the flux generated by the field windings. So for example, we are increasing the field resistance, increase in RF, increase in RF, that is the field resistance, means the field current, which is equal to the field voltage divided by RF. Since RF has increased, IF will decrease. So that means IF decreases. As we increase the field resistance of the field windings by having an adjustable, we can basically incorporate a rheostat in the field windings, and by means of that we can increase the field resistance. It's possible for us to increase the field resistance comparatively much easier because we can place the rheostat in series, and placing the same resistance in parallel becomes a little bit tedious task in any kind of machine. Fine. So we are increasing the field resistance, that means IF will decrease. Now with IF decrease, as IF decreases, this implies flux decreases as well. The flux produced by this system will decrease. Now we know that the induced voltage in a DC machine is equal to K phi omega. Since omega is decreasing, which implies if phi decreases, EA will decrease as well. Go step by step, increase the field resistance, IF decreases. IF decrease means the flux decreases. Flux decrease means that the induced voltage in the motor EA will decrease as well. We have seen last time that EA VT is equal to EA plus IARA, which implies IA is equal to VT minus EA divided by RA. Since EA is decreasing, that means IA in the system will increase. Number E. Now IA is decreasing. Now we know what is the induced torque in the DC machine. The induced torque in the DC machine is called K phi IA. Fine. Now if you look at the induced torque in this case, what happens is that the flux decrease is less as compared to the increase in armature current. That means the magnitude of change of armature current is more as compared to the magnitude of change of increasing, and the increase in magnitude of armature current is more as compared to decrease in the magnitude of field flux. That means, which therefore implies induced torque increases as well. This point is important here. We are saying that torque induced is equal to K phi into IA. Here now you can see that flux has decreased but armature current has increased. So which way should this go? Should this be constant or should there be a change in the induced torque? What we can see is that the magnitude of change in flux is less as compared to the magnitude of change in the armature current. The armature current has a more dominant effect, and therefore the induced torque is increasing. We can actually use a simple example to illustrate this, how the flux has basically, how the increase in flux is much, how the decrease in flux is less as compared to the increase in armature current. We can use it, we can have an example here. So as an example what we can take is, let's have a motor and a shunt motor. This is its armature winding and the field windings, and this is its we are applying the voltage from this side, Vt. Fine. This is the variable field resistance, and let this voltage be equal to 100, say for example, and let this voltage be equal to 90 volts. Fine. And let this resistance be equal to 0.1 ohms. Fine. So what will be the armature current? IA we know is equal to Vt minus EA divided by RA, where Vt is equal to 100, EA is equal to 90, and RA is equal to 0.1. So this is 10 divided by 0.1, that's equal to 100 amperes. Fine. So this is just an example. Now let us assume the flux decreases by say for example we are saying the flux decreases by 1%. Fine. So 1% decrease in flux means since we know that EA is called to K phi omega, K and omega, let's assume they are constant. Flux is decreasing now. That means our new EA dash will be equal to K phi dash omega, where phi dash is what? Where phi dash is since phi has decreased by 1%, that means it is actually 0.99 of the initial phi. Fine. So K phi omega was the actual armature voltage that was equal to EA. So this is 0.99 into EA, where EA is already given to us, is equal to 90 volts. Fine. So 0.99 into 90. That's equal to 89.1 volts. Fine. So our new EA with a decrease in flux by 1%, our EA, that is the induced EMF in the system, also decreases, and our new EA is equal to 89.1 volts. That means our new armature current will be 100 minus 89.1 divided by 0.1, that's equal to 109 amperes. Fine. So initially our armature current was 100 amperes. Now our armature current has increased and it has become 109 amperes. So how much increase in the armature current have we obtained? That is equal to 109 . So we see an increase in 9% in IA. Fine. armature current has increased by 9%. It was initially 100 amperes. It has become 109 amperes after the flux was decreased by 1%. So 1% decrease in flux results in 9% increase in armature current. So that's why the induced torque that I had written here will increase, because the magnitude of change in armature current will be much more as compared to the decrease in the field flux. So this is step number 5. So far we have seen that we have increased the field resistance. Increase in field resistance means the field current decreases. Field current decrease means what happens is flux produced will decrease. The flux produced decrease means induced EMF EA will decrease. EA decrease means IA will increase. IA increase, flux decrease means torque induced will increase. So if torque induced is now actually more than the load torque, that means the speed of the motor will increase. So we are not loading the system as much because the load is same. Whatever was the load initially, that is same. We have only changed the field resistance. We have increased it so that the flux decreases, so that the torque induced basically increases in the system. So since induced torque is much more as compared to what the load is actually right now on the system, therefore the motor will speed up. Right? So it basically speeds up. So this means the motor is the speed of the motor increases. Now what happens subsequently is, as the motor is increases in speed, initially what was the case? Phi had decreased, so EA had decreased, but now speed has increased also. So once the speed increases, that means EA will again increase in the system. EA increase means IA will decrease and torque induced finally. EA increase means IA decreases in the system, and therefore once IA decreases, torque induced will now again finally be equal to the load torque, but at what expense? At increased speed, at the expense of increased speed. So this balance has been achieved back into the system only because the speed of the motor has increased. So initially what is the case? If the motor, if we say this is speed and this is time, and say for example the motor was running at 100 RPMs, fine, so it was running at 100 RPMs. So because in change in field resistance, there will be a momentary change and the speed of the motor will increase because of this, because of the change in the field resistance. We have basically been able to increase the speed of the motor. It will finally achieve steady state again, but this steady state, this basically refers to the steady state condition where our induced torque and our load torque are again equal, but this steady state has now been achieved at the expense of increase in the speed of the motor. Now second method of changing the speed of the DC shunt motor is changing the armature voltage. So this is a fairly simple method. We are increasing the speed of we are actually increasing the terminal voltage feeding the armature of the DC shunt motor. So what happens with the increase in armature voltage? Increase the armature voltage, the terminal voltage, that's Vt. Now we know what is Ia equal to. Ia is equal to Vt minus Ea by Ra. So if Vt increases, that means Ia increases as well. Fine. So if the Ia in the system increases, the induced torque that's equal to K phi Ia. In this case, flux is constant. We are not changing the flux of the system. Since Ia increases, torque induced torque also increases. So since the induced torque is greater than the load torque of the system, that means the speed of the motor increases as well. So the load on the motor is same, but the electromagnetic torque that was induced in the system has increased. That has to and what the effect of increased electromagnetic torque in the system means is the speed of the motor increases. Fine. Once the speed of the motor increases, we know that what happens to Ea being equal to K phi omega. As omega increases, Ea will increase again. Once Ea increases, that means the armature current decreases again. Looking at this equation, Vt was initially we had increased Vt only. Now Ea also increases. That means increase in Ea means decrease in the armature current. Right. So once the armature current decreases, finally the induced torque that's equal to K phi Ia will again be equal to the load torque, but at what expense? At the expense of increased speed. So these are two methods that we can employ for armature, for changing the speed or controlling the speed of a DC shunt motor. One is the field control method. In the field control method, we change the field resistance. Fine. And second one is the armature control method. In the armature control method, we change the armature voltage feeding the DC shunt motor. So both will cause increase in RF causes increase in speed, increase in armature voltage causes increase in speed. Similarly, decrease in RF, if possible, will cause decrease in speed. Decrease in armature voltage will cause decrease in the rotor speed of the DC shunt motor. Having said this, the third method that we had listed was changing the armature resistance. How we can change the armature resistance? By incorporating another adjustable resistance in series with the armature winding. So what happens in this method? So in this method, as we know, Ia is equal to Vt minus Ea divided by Ra. An increase in armature resistance means decrease in armature current. A decrease in armature current means your induced torque, that's equal to K phi Ia, torque induced also decreases. And as torque induced decreases, that means torque induced becomes less than the load torque. That means the speed of the motor decreases. Fine. The speed in the motor decreases means Ea will decrease. Ea decrease means Ia will again increase. That means again then torque induced will be equal to torque load. The steady state will again be achieved but at the expense of decrease in the rotor speed. Now this method is not preferred because increase in the armature resistance means basically increasing the power losses. Increase in armature resistance causes increase in I square R losses. That means power losses are more. Fine. So this method will not be used. Armature resistance is actually very small. It can be of the order of 0.3 ohms. Field resistance, as it is in shunt, we basically use a larger field resistance, 100 ohm or 150 ohm resistance. Fine. So even if we increase that by 10 ohms, 20 ohms, increase in field resistance does not contribute to the power losses in the system. But even if we increase the armature resistance, say for example from 0.2 to 0.5, there will be significant amount of increase in the power losses in the system. So these are your three methods of speed control as we have in case of the DC shunt motor. Now now there are two methods. So we have discussed two methods: the field control method and the armature control method. In the field control method, so we have seen that by increasing the field resistance, the field current can be decreased, and as the field current decreases, RF increase means IF decreases, and it causes the speed of the motor to increase. Fine. What we do is we normally use this method for controlling the motor speed above base speed. Fine. So say for example a motor can operate from 0 to 200 rpms. Base speed will be of 150 rpms. So why we will operate the using field control strategy, why we only operate the motor for achieving the speed of the motor above base speed? Because a decrease in RF means increase in field current, and since there is this decrease in RF will cause a significant amount of change in the field current, there will be a limit to the field current. IF is limited. We cannot increase it beyond a certain value above which basically it will cause the windings to burn. Since RF is already large, a decrease in RF will cause significant increase in the field current, and we cannot go beyond a certain rated value of IF. That will cause the motors will be basically damaged. So there will be a limit to which we can actually operate the motor under field control method. That will be the base speed. Above base speed we can easily increase the value. We can keep on increasing RF so that IF decreases. There will be practically no limit to decreased IF. Only the thing is now physically what the motor will be able to handle, the mechanical bearings of the motor will be able to handle. Accordingly we can decide how much speed we can go up to by the field control strategy. As far as the armature control strategy goes, what we see is by decreasing the armature voltage, the speed of the motor decreases. An increase in armature speed causes an increase in the speed of the motor. Practically there is no limit to decreasing the armature voltage. We can decrease the terminal voltage up to 0. The speed of the motor will be 0 at that time. but there will be a limit to which we can actually increase the voltage. We cannot go beyond a certain rated value of voltage. It will again cause the machine to damage. So this method can be used for controlling the motor speed below base speed values. Fine. Vt can be decreased up to 0, so that speed can be 0, but Vt, say for example, the rating of this motor is 230 volts. We can go up to 240, 250 volts at max, but beyond that we will not go, because it will cause the there's a rated value of the voltage that this machine can actually bear. So field control strategy will be used. These two will basically now be used together so that the motor operates more efficiently, and there is a better speed control achieved in the motor. So we'll use field control for controlling the motor above base speed, and we'll use armature control to control the motor below the base speed. So what you can see is, if this is the base speed, in this region we'll use the armature control method. In this region we'll use the field control method. Once you see the equations, you'll notice that the torque in the armature control, while maintaining the field flux constant in this region, the torque will be constant, and then it will start decreasing in this region. And similarly, power will be constant in this region. Power will be increasing in this region, and then it will be constant in this region. So this is power profile, this is your torque profile. So this will be the maximum torque you can derive from the system, and this will be the maximum power that you can derive from the system. This is the output power of the system. P is equal to tau omega. Omega is increasing, tau is decreasing, therefore power is constant in this region, whereas in this region, in 0 to W base, power is increasing, speed is also increasing. P is equal to tau omega, therefore tau is equal to P by omega. Torque will be constant in this region. So this is about the shaft power and the shaft torque. Using this equation, you can basically see from 0 to W base, speed is increasing, power is also increasing, therefore torque will be constant, while as after W base, now there will be a limit to it will be now limited. The power can no longer increase in the system, torque is decreasing, and omega is increasing, therefore power in the system will now remain constant. So this is the profile, the power and torque profile of a DC shunt motor for the armature control method and for the field control method. So this is about the speed control of DC shunt motor. Next we'll take up separately excited DC motor, study its speed torque characteristics, and also see how we can control the speed of the separately excited DC motor.